Okay, so welcome to this review session of HE3023 Econometric Analysis for Financial Data. So in this review session, I'm going to go through the key points of the topics we covered in this course. And as I said before, since we're not going to test the VAR and panel data for the final exam, so I'm mainly going to go through topic 1, 2, 3, 4, 5, 6, 7, and 9. Okay, so let's first look at topic 1. Topic 1 is Introduction to Financial Data. So it's a pretty short chapter. So in this chapter, firstly, we looked at the definition of discrete returns and continuously compounded returns. So the discrete returns is just something like the simple returns you have studied before. So it's just like the change of the price divided by the price of the last period. And continuously compounded return is like the D-log return. So calculated more like difference between the natural logarithm of the price of today and yesterday. And the second key point we covered in this topic is the skewness and kurtosis. So you should know the definition of it. So I wouldn't ask you to do calculation for skewness and kurtosis, but you should understand what does like negative skewness and positive skewness mean, or left skew or right skew mean. And for kurtosis, you should also know it's more or less like a peakness, a measure of peakness of a distribution. And usually we compare it with 3 because 3 is the kurtosis for the normal distribution. Okay, so and after that, I showed you this Yakubara test. It's a formal test for whether distribution is like a normal distribution. So there is a measure for it. I wouldn't ask you to calculate the measure, but in general, you should know the idea of the measure is more like it measures the deviation from a normal distribution. And when this Yakubara test statistic is big enough, usually we reject a null hypothesis that the distribution is a normal distribution, and which also should suggest that the distribution is not a normal distribution. So I think that's the most important thing you need to know about Yakubara statistics and Yakubara test. Okay, and finally, I also draw some relation between kurtosis and fat tail in financial data. So you need to understand that bigger kurtosis, like large kurtosis, does not only mean higher peakedness of a distribution, but big kurtosis is also associated with fat tail in financial data. So that's more like the key points of topic 1. And then let's look at topic 2. Okay, topic 2 is the introduction to finance theory. And in this chapter, in this topic, we mainly pay attention to, I think, 2 important theories, like 2 benchmark or standard theories in finance course, namely the efficient market hypothesis and the CAPM model. Okay, so the first point is, of course, about the efficient market hypothesis. The efficient market hypothesis, remember, just like if we want to say it in short, efficient market hypothesis means that there is no free lunch on the financial market. So in general, it's very difficult to use the existing or available information to predict future market prices and hence earn a profit. So there are also kind of 3 forms of market efficiency: weak, semi-strong, and strong form. And you should also know that if market efficiency holds, then basically it means that you cannot have more return without taking excess risk. So this is also something like the intuition behind the common saying about there's more risk, and so you need to, if you want to have higher return, you need to take more risk in the financial market. So these are the main intuition for the efficient market hypothesis. And after that, I briefly mentioned some kind of evidence and something like anomaly for efficient market hypothesis. And among them, I think a very important point will be the empirical evidence for market efficiency from event study on earnings announcement by McKinley. So it's more like, you remember, there is a graph, right? There's a graph. So it's a graph. So event study is more like you draw the CAR, like accumulated abnormal return for the asset, right? So there is a kind of a day zero. Day zero is the event date. In this case, that will be the date on which the earnings information is announced, right? And also in this graph, it's the news or the announcement is divided into good news or no news or bad news. So basically, if market efficiency holds in general, you should see something like, like if the weak or semi-strong form of market efficiency holds. So basically, you should see the CAR, the cumulative abnormal return, is kind of flat before the announcement date, and on the announcement date itself, suddenly it should jump up for the good news and jump down for the bad news, and should stay the same for no news. But actually, I think in general, from the graph, if you remember it, we also see something like, okay, so in general, it supports market efficiency, which means that around the day zero, in general, the market, so the return tend to go up for good news and tend to go down for bad news. And we even see some kind of a hint for a strong form of market efficiency, which says that the market even started to increase before the date of announcement for good news, or it already started to go down a little bit before the day of the bad news. And moreover, we also see something like overshooting at the beginning or overreaction at the beginning for bad news, and something like that. So you should be familiar with what happens on that graph. And after that, we also have the CAPM model. So CAPM model, so basically to derive it, we have several portfolio theory, but in general, it's a little bit complicated. You just need to know that, well, basically the idea is that if you have a large portfolio, right? If you have a large portfolio, the main part of the risk of the portfolio doesn't come from the individual risk of the individual assets, but more from the correlation between the risk of the different asset in the portfolio. And in the end, if you want to have a very good portfolio where the risk is sufficiently diversified, in general, you should go for the market portfolio, which is really a good portfolio. And in equilibrium, if all the assets are priced right, you should have this CAPM model. So basically, where the return, excess return of each asset, excess return is calculated as the difference between the return of this asset and the risk-free asset, right? So the excess return of each asset should only depend on like its correlation, more or less its correlation with the market portfolio. And basically, there is a measurement or a coefficient beta. So it measures the correlation between the asset and the market portfolio. And in general, if the asset is more correlated with the market portfolio, when there is 1 unit increase in the excess return of the market portfolio, then the excess return of this asset should also increase faster. So if you want to do that empirically, remember this, that's similar to what we have seen in the exam question, right? So but usually we estimate the CAPM model using this kind of excess return of each asset is equal to alpha plus beta times excess return of the market portfolio, right? And if CAPM works, in general, alpha should be 0, or from econometrics point of view, alpha should not be significantly different from 0, right? And for beta in general, we also divide into the case where you have aggressive uh, asset where the beta is larger than 0, and defensive asset where beta is smaller than 0. So you should understand in general the meaning of the CAPM model and should be able to explain the estimation result of a CAPM model. Okay. All right, and then we go for topic 3. That's the review of basics of econometrics. So that's, I think, well, there is some repetition of what you have learned from the previous course, but we also add some new things. So that is why I highlighted the relatively new things in this course as a key point of this part. So firstly, I want to emphasize that you don't need to be able to calculate how to estimate beta 1 or beta 2, or you don't need to remember the equation for B1 and B2, but you should understand, you should know when are the estimators B1 and B2 more accurate, or you should understand that B1 and B2 they are not two constant, they are actually two random variables, and there are some conditions for their variance to be smaller. So you should understand this is just on the slides of the lecture. And the second key point says that why do we sometimes prefer to use log linear or log-log models? So basically, you should remember that when you take log in general, the numbers become smaller, right? And also usually you change the meaning of the marginal effect. So before it's more like a marginal effect of just kind of a unit change, the relationship between unit change. But if you change it to log term, it generates the meaning change to relative term or percentage. And you should also know that when you take log of especially some variables where you usually have very big numbers, for example, GDP, and if you take log of them in general, the numbers become, firstly, the values become smaller, and secondly, it becomes less spread. Then it implies that by taking log, it also implies that usually you make the distribution of a variable closer or more similar to a normal distribution. So that's also part of the reason why we want to take log when we do some estimations. Okay, and the next, I think you should remember the formal steps for doing a hypothesis testing for econometrics. So you should remember the steps. So for a formal test, you should know that you should first set up a null hypothesis and the alternative hypothesis. So basically, you should have H0 and H1. And second, you should find the related test statistic. Either it is a t statistic or chi-square or f statistic. You should decide on that. And thirdly, you should find the critical test statistic like the critical t or critical chi-square. And you should also pay a lot of attention to, let's say, if you want to do a t-test, right? The t-test can be one-sided or two-sided. So in this case, you should look for the right critical level of t statistic. And finally, you compare your test statistic and the critical level of it and draw a conclusion. So basically, if I ask you to do a formal t-test or a chi-square test, you should present the 4 steps completely instead of just looking at a p-value. I mean, if I don't ask you to perform a formal test, of course, the easiest way to draw a conclusion of something is to just look at the p-value, whether the p-value is larger than 0.05 or smaller than 0.05. But if I ask you to do a formal test, you should give me the complete steps. Okay, that's very important. And after that, here we have cross-sectional models and heteroscedasticity. So here by cross-sectional model, we mean that it's a multivariate regression model. So basically, when we do the review was mainly about so-called simple regression, which means that you only have, let's say, one x variable on the right-hand side of the equation. But in this cross-sectional part, when you have multivariate regression model, it means you have more than one independent variables, more than one x variables. And in this case, you should also know when are the least square estimators more accurate, or when do they have smaller variance. The conditions are very similar to the case in chapter 3, or for the case for simple regression. There's just one additional thing about the correlation between the variables, and that's something you should know. And after that, I also said something about the f-test. You can do f-test, especially for OLS models. F-test is usually used when you want to test joint hypothesis, which means that it's not only testing for one coefficient, not only testing for the constraint for one coefficient, you also test the constraint on several coefficients, or you test several constraints at the same time. So basically, the intuition of f-test is that when you put constraints, you always decrease the fitness of a model, and hence you should have larger sum of square residual, right? And if you go from unrestricted model to restricted model, then if the restrictions are reasonable or good, then you should see that the sum of square residual doesn't change or doesn't increase by a lot. But if you see a big increase in the sum of square residual, which is associated to a much poorer fitness, then you should reject the hypothesis that you can throw in those constraints or restrictions. So basically, you should understand the meaning of f-test. And if I give you, let's say, the sum of square residuals of the restricted model and unrestricted model, as well as the j and minus k, you should also be able to calculate the f statistic. Okay, that's for f-test. And after that, here is a problem for omitted variables. So in general, when we run the least square models, it's likely that some of the times we miss some variables that also helps to explain the dependent variable. And I think you should notice that omitted variable, usually if you think about it, we can never have a perfect model. So basically, when you run the regression, it's usually the case that you almost always miss some variables. But when we talk about omitted variable is only a problem if the variables that you miss, firstly, the variables you miss also helps to explain why or explain dependent variable, and secondly, the variable you miss has some correlation with the x variables already in your model. So those are the two conditions for omitted variable to happen. So suppose you have some variable that also help to explain y, but is uncorrelated with the x variables in your model, then there is also no problem of omitted variable. So just refer to the case like the example we had in the slides. We have the number of rooms, number of bedrooms of apartment, and the area, right? So basically, if you don't have the area in your model, but just have the number of bedrooms, so you have the problem of omitted variable. You have the problem of omitted variable not only because the area of the apartment helps to explain the price of the housing price, but also because the area of the apartment is associated or is strongly correlated with the number of rooms in your apartment. So that's very important. Okay, and the consequence of having omitted variable, you should know that when you have omitted variables, it's a pretty big problem because in that case, that can lead to biased estimator. So your estimation may be biased. And there is also a test for omitted variable. That's the reset test. And reset test is an F test. The null hypothesis is you don't have omitted variable, and if you reject, it means that you have omitted variable. Okay, and the fourth point of this lecture is the heteroscedasticity. So firstly, you need to know what does it mean. It means that your variance of the average term of your regression is not a constant, but the variance is correlated with some variables. In particular, usually it's correlated when we say there is a heteroscedasticity, most often when the squared error term is correlated with the independent variables. That's the most commonly seen case. Okay, so when you have heteroscedasticity, it doesn't lead to bias of estimators. So basically, when you have heteroscedasticity, the estimators are still unbiased, but it just makes the variance not right, and hence your test statistics are not right. So in general, it's a less, you can say that it's a less severe problem compared to omitted variables. Okay, and if you want to test for it, the test we use is the Y test. And so basically, you just run an auxiliary regression using the variance of the error term as the dependent variable and some candidate variables, for example, the independent variables of the model as the independent variable, and see whether this regression has a very big R square, right? And if you see a very big test statistic, which is the n times R square, and if you see, let's say the p-value of the Y test is less than 0.05, that's an indication for heteroscedasticity. And if you have the problem of heteroscedasticity, there are two potential ways to address it. First one is you can apply weighted least square, and second possibility is you do the regression with wide robust standard error. And you should also know that when you do weighted least square, it solves the problem of heteroscedasticity. If you just use wide robust standard error, it doesn't really remove the heteroscedasticity, but it just gives you the right test statistic. So there are two. So the result of the two solutions are a little bit different. So in particular, you should know that wide robust standard error doesn't remove the problem, but it only report the right test statistic when the problem is still there. So that's about the wide robust standard error. And then let's look at topic 5. Topic 5 is about indicator variable and discrete choice models. So basically, both models in this chapter are about the case where the variables can take the value of either 0 or 1 instead of being a continuous variable. So first, we discussed about models with dummy variables. So of course, you need to understand the meaning of the coefficient in these kind of models. You need to understand the meaning of coefficient for dummy variables. So in general, it means something like the difference between the two groups. So for example, if you have a dummy for the gender, let's say 1 for female and 0 for male, you should know that then the coefficient for this female dummy measures the difference between female and male. Okay. And after that, we also mentioned briefly the DID model, differences in difference model. So it sounds a little bit complicated, but in general, you just need to know because it's very commonly used for policy evaluation and so on. So at least you need to know roughly the meaning, which is something like, okay, so in the DID model, you just have two dummy variables, right? You have the time dummy and treatment dummy. So treatment dummy is 1 for the treatment group and 0 for the control group. And time dummy is more like 0 for before and 1 for after. And if you put the two dummy variables and the interaction term into the regression, right, together with a constant, then the coefficient for the interaction term between treatment dummy and time dummy should measure the treatment effect. Okay, and after that, I introduced to you the discrete choice models. So basically, discrete choice models is different from dummy variable models, right? So for dummy variable models, it happens that the x variables takes either 0 or 1. But for discrete choice models, it usually means that y has discrete uh, realizations. And for most of the time for this course, we just say that discrete choice model means y takes the value of 0 and 1. Okay, and there are a few ways to estimate discrete choice models, right? And you can do linear probability model, or you can also do a nonlinear one, which is either a probit or a logic model. And first of all, you should understand that if you do linear probability models, the good thing is that for linear probability model, the meaning of the coefficient is again pretty intuitive. It just measures like when there is one unit increase in x, what is the increase in the probability for something to happen, for the y variables to happen. That's something good. But at the same time, there are quite some drawbacks for the linear probability model. For example, the most important case will be that the prediction of a linear probability model can be larger than 1 or smaller than 0, which is quite kind of counterintuitive or so hard to understand for probability. So it can give you predictions outside of 0 and 1. And also, by definition, there is also a problem of heteroscedasticity. So you should refer to the slides about the drawbacks. And when we know that there are some drawbacks of a linear probability model, we can do nonlinear models like probit and logit. So the advantage of both probit and logit is that since we have the probit function and we have the cumulative distribution function of normal for probit model, and we have the logit function for logit model, due to the shape of the function, the realization of y, or the realization of the probability, is always between 0 and 1. So we guarantee that when we do probit and logit model, the predicted probability is always between 0 and 1. But at the same time, there is something tricky about probit and logit model. This is also something we have already said in the lecture, which is that it's a little bit difficult to explain the coefficient in the probit and logit model in terms of marginal effect, because remember when we look at the slides, the marginal effect of x on y is actually the coefficient beta times something like the PDF function. So basically, at least in short, you need to know is that the marginal effect of x on y, marginal effects of x on the probability, is not constant. It's changing everywhere, and it tends to be big when the guy inside of the bracket is close to 0, and it tends to be small when the linear term in the bracket is either very big or very small. So you need to know that you cannot just interpret the coefficient before x in the probit and logit model as the marginal effect of it. And finally, there is a third point where we also said that since it could be inconvenient when we cannot use marginal effect for probit and logit models, so people also invent this concept of average marginal effect. So basically, then they just take average of the marginal effect of x, or of 1 unit change of x on y for the whole range of the function. And in that case, if you are told the average marginal effect of an estimation, though you can at least make some rough estimation saying that if I tell you, let's say the marginal effect, average marginal effect of a probit and logit model is 0.03, then you can say that, well, it says that on average when x increased by 1 unit, then the probability will increase by 0.03 or 3%. So that's the use of average marginal effect. Okay, and then we come at topic 6 or lecture 6. It's about serial correlation and ARDL model. So first of all, we need to look at, we studied serial correlation. I showed you these two pictures about how a typical time series with positive and negative serial correlation look like. So you should roughly remember the shape. And then I introduced to you the Durbin-Watson test. So basically, Durbin-Watson test is a rigorous test, but it's a pretty kind of a rough test. You should know that it's a kind of it has a limited scope, firstly. So it can only be used for what? It can only be used to test the AR1 serial correlation. So only the correlation of the error term for its first leg. And secondly, for this course, I only require you to know how to use Durbin-Watson for positive serial correlation. So even though you can use a transformed Durbin-Watson also for negative serial correlation, but in this course, since there are a few tests, I only require you to use Durbin-Watson for AR1 serial correlation and AR1 positive serial correlation. Okay, and you should also know the kind of intuition of Durbin-Watson. So basically, the value of the Durbin-Watson statistic is always between 0 and 4, right? Or roughly speaking, if the AR1 coefficient is rho, Durbin-Watson statistic is kind of 2 times 1 minus rho. And from this equation, you should know that basically when rho is very big, Durbin-Watson tend to be very small. So basically, when you see a very, very small Durbin-Watson statistic, let's say it's less than 2, then it's more like an indication for AR1 positive serial correlation. So that's for Durbin-Watson. And after that, we also studied Bridge-Godfrey test. So it's an LM test. And you can calculate the test statistics like T times R squared, right? So it's a number of observation times R squared of the auxiliary regression. And it follows chi-square distribution. And the degree of freedom Q is the number of lagged error term you have in the auxiliary regression. So you should know all of this. And after that, so suppose you perform Durbin-Watson, or you suppose you perform Bridge-Godfrey and find there's a serial correlation, right? So you need to know that what's the consequence. So the consequence is similar to heteroscedasticity. So basically, you still have unbiased estimator, but at the same time, your test statistic is not correct. So in order to address this problem, you can also do weighted least square, but the weighted least square for time series is a little bit too complicated, so I didn't include it here. Or you could also use HAC or New US robust standard error. And also you need to know that when you use this kind of robust standard error, it's always the case that you don't really remove the problem of serial correlation, but you just ask the software to report the right test statistic, given that the problem, the serial correlation is still there. So you should know this. And secondly, something special about HAC or New US is that you should know when you do New US, you not only remove serial correlation, but also you also remove heteroscedasticity at the same time. Okay, so it's not like white. White only deal with heteroscedasticity, but New US deals with both serial correlation and heteroscedasticity. Okay, and after that, I also introduced to you the ARDL model. So ARDL model is like when you run the regression of y and x, you also throw in the legs of y and legs of x on the right-hand side of the equation. So by doing ARDL in the right way, by including the right number of legs of x and y, you can also remove serial correlation. So the intuition is just like, remember what I said in the lecture. So if you have, let's say, if you know that the serial correlation is like AR1, so the error term is correlated with its first leg, then because you can rewrite the error term of the first leg as a function of the first leg of y and x. So in that case, if you do an ARDL, including the first leg of y and x, basically you control for this. When you control for this, you also remove the effect of the first leg of the error term. So that's the intuition for why ARDL can remove serial correlation. And after that, I also said that, okay, so I do require you to be able to do some calculation for ARDL model. You should be able to do delay multipliers and the total multiplier for ARDL model. So this kind of calculation will be also similar to the question in the example exam, which I already posted and discussed. Okay, and after that, I briefly mentioned AIC and BIC, right? AIC and BIC. Maybe some of you also have studied that in the course for AMA in the content for AMA. And in this case, AIC and BIC can also be used to select the right number of legs for ARDL model. So AIC and BIC basically they measures is also something like the weighted average of the fitness of a model, and also with some punishment term of the number of coefficients in the model. So you just need to know that I think so basically a measure if you compare nested models, so basically when you add more variables into the model, you should just look at how AIC and BIC change, and in general they are inverse measure of the fitness of the model, and basically in short they are the smaller the better. So basically if you want to see what is the optimal number of legs to include in an AMA model or ARDL model, so you should basically just look for the smallest AIC and BIC. Okay. And then let's look at chapter 7. So in chapter 7, we studied stationarity and co-integration for time series models. Stationarity is a very important concept and problem for time series regressions. So suppose you have non-stationary time series variables, then if you run a regression between them, you easily have the problem of bad regressions. So in general, if you want to have reliable results, you should only run regression using stationary variables. Okay, and in this chapter, we focus on first how to test for stationarity of time series variable. We discussed the Dickey-Fuller test or augmented Dickey-Fuller test. It's a test for unit root. So if there is a unit root, then it means that this time series is not stationary. And if you reject the null hypothesis of unit root, it means that there is no problem of non-stationarity. So basically, as I also said in the lecture, it's a little bit different from many other tests in econometrics. So basically, for most other tests, for example, the heteroscedasticity test, the null hypothesis is always like there's no problem. So okay, so for heteroscedasticity test, the null hypothesis is there's no heteroscedasticity. But stationarity test is pretty special. The stationarity test or Dickey-Fuller test has the null hypothesis of unit root. So basically, just for this test, you have a problem. So you have a problem under null hypothesis. So basically, the time series is not stationary under null hypothesis, and your time series is stationary only when you reject the null hypothesis. So that's something pretty special about Dickey-Fuller test. Okay, and then we also discussed the order of integration or order of integration. So I1, I0, or I2, what do they mean? So basically, this means that how many times you need to take difference before this time series first become stationary. So basically, I0 is stationary as it is. I1 is not stationary, but it is stationary after you take the first difference. I2 is not stationary. The first difference of I2 is also not stationary, but if you take the difference twice, an I2 time series also becomes stationary, and so on. And finally, we discussed the co-integration model. So basically, as we said at the beginning of this chapter, if the time series are not stationary, in general, you cannot run a regression on them. You need to take differences. But in some of the cases, we may be able to estimate a model with unstationary time series, and that's the case when we have co-integration between the variables. So in general, suppose we have a few I1 variables. So it only happens when you have I1 variables. If you have a few I1 variables, and if you run a regression between them, and if the residual is stationary, then we say there is co-integration between these variables, and you can still run this kind of regression. Okay, that's the key idea of co-integration. And for this kind of co-integration, why do we want to have it? One of the main reasons is that when you take difference, you lose degree of freedom. So basically, because kind of a degree of freedom is valuable, so that is why if you have co-integration with time series models, some of the times people prefer to estimate co-integration model instead of taking differences to save some degree of freedom. That's one of the most important motivation. And I also said there is a Granger-Engel co-integration test. So basically, it's just something like a Dickey-Fuller test. So it's just like when you run the regression between those I1 variables and then test whether the error term is stationary. Okay. And after that, we also said for a full co-integration model, it actually consists of two parts. So the first part is the regression itself, and second part is what we call error correction model. So basically, you estimate the change of y on the change of x and also the error in the last period. And basically, we say that the main regression is more like the long-run relationship between y and x. And the second error correction model is something like the short-run adjustment between the two variables. And preferably, when we have the error correction term, right, when we have the error of the last period, the coefficient before it should be negative. This is something we said. It is negative because it should be negative because then it will suggest that, let's say, if the y was too high or too low in the last period, then the error correction model will drive it down or drive it back up so that it goes back to the levels which is suggested by the long-run model. So you should also read this part of the slides very carefully. Okay, so that's the key points for topic 7. And finally, we have the topic 9. Topic 9 is the time-varying volatility and arch models. So basically, this is also some new stuff in this course. Right at the beginning of this chapter, I also mentioned something like the difference between conditional and unconditional means and variances. So those are for illustration, right? So you should understand that for real time series data, it's pretty easy for you to see that the conditional variance of some time series is changing over time. So that is part of the motivation why we want to have a model that captures the time changing or time varying volatility. Okay, so so the basic part of arch model, right? So basically, the very basic arch model is like you can just regress the y on the constant term, right? There's just one long run mean, and then you have the conditional variance of this period called HT. HT can be a function of, let's say, alpha 0 plus alpha 1, ET minus 1 hat squared. So basically, it says something like when you have larger variance of the regression in the last period, you should also have larger conditional variance of today. So if you have larger square error term of last period, you should also have larger conditional variance of the regression today. Okay, and then we also briefly we also briefly discussed how to test for arch effect, right? We also discussed briefly about how to test for arch effect. So basically, you can just run the regression, find the residual E hat, right? ET hat. You can run the ET hat squared against the constant, and also like et -1 hat squared, like the square term of the past error term, and see whether the coefficient of the past square error term is significant or not. So it's also in the slides. And after that, we also studied briefly so-called T-Gauge model. Well, I also discussed a little bit about Gauge model. So, but for Gauge model, basically the derivation is quite complicated. So you just need to know that. So Gauge model is more like the AMA version of the arch model, right? So in the arch model, it's just like the HT, the conditional variance is a function of past square error, like HT is a function of past term of ET hat squared or ET squared. But in the Gauge model, it will be more like the HT is not only a function of past ET squared, but also a function of the lag term of itself, like HT minus 1, HT minus 2, and so on and so forth. So, and for T-Gauge model, that's a pretty special model, but it's quite relevant for empirical data, because if you think about it, in real life, right? So if you think about the changing volatility, when does the volatility increase more? So you can easily understand that the volatility tends to increase more when there's bad news compared to good news, because bad news may generate panic, but good news probably may not generate that strong emotion of the market. So that is why if you do a T-Gauge model, right? So usually you also have, let's say, a dummy variable for bad news of last period, and here the bad news is measured by the actual term of the main regression is less than 0, right? So the realized return is below expectation. And in this case, you should see that the coefficient for the dummy variable for bad news times the past square error or past square error should be a positive term, which says that when there was bad news in the last period, then when there's 1 unit increase in the square error term of last period, then the conditional variance tend to increase more. So it's also in the slides. You can read it for more details. And finally, we have the Gauge in the mean model. Gauge in the mean model also captures kind of the intuitive idea that in the market, the people should require excess risk or risk premium for the risk they take, right? So basically, in this case, the Gauge in the mean basically says that when you have larger conditional variance, in general, the return should also be higher, because people want higher return for taking more risk. Okay, so this will be the knowledge point for chapter 9 or topic 9. Okay, so that's more or less about the key knowledge points of each chapter, but of course you also need to go back and study the slides and past exercises very carefully. And yeah, so basically that will be the content for this review session, and I hope all of you very good luck for the final exam.